find the last one somewhere. We can close it out. I believe, Aaron, you got your PhD from ETH, right? But the Frankfurt Bosch on diameter model. We can talk about some of the stuff today on dark hill.
Thank you. Okay, so this is some work I've been doing as a CITA fellow in University of Victoria. So it's in 2 papers. These are all the list of people who worked mutually exclusively in these projects. There's a common theme which I'll describe. Okay, so the motivation basically, well, first I'll give an outline. The motivation basically is trying to understand what dark matter is. And then there are these 2 key unknowns, which are quite cool, dark energy contraction and Stellar IMF. And then I'll talk about results from these 2 papers. One, results from scaling relations, such as the Tully-Fisher and the Baker-Jackson relation. And then other more recent results from Sloan Lens. Okay, so the basic motivation is, what is the dark matter in the universe? It's 84% of the mass, if you ignore the energy component. So it's quite dominant. And we don't know what it is. So the dark matter requires new physics. It's either some new dimension particle, or maybe more exciting, so it will be modifications to gravity. So one way you can constrain the nature of dark matter is by the distribution of dark matter on non-linear scales, which means galaxies. So there's 2 questions. One, how does theory predict the dark matter distribution of galaxies? So I'll describe that a bit. And then how do we measure the dark matter distribution of galaxies? And then the key unknowns in answering these 2 questions is, how do the LCDM and halos respond to galaxy information? And what is the initial stellar mass function of stars? Okay, so this is in the background sort of fake. This is a picture of the Millennium simulation part of it. So over the past 10 years or so, cosmological n-body simulations have sort of grown into a mega thing, and they now precisely predict the structure of cold dark and halos as a function of cosmological parameters. And so these are just some of the names you've heard of: Millennium, Millennium 1 and 2, Galaxia, Bolshoi, and Aquarius. So the 2 basic predictions. One is the density profiles are universal, in the sense that they can be described pretty well by this double power law with an inner slope of -1, which is its cusp, and an outer slope of -3. And then the other key property of these halos is the concentration mass relation. So concentration is just a way to express the scale radius in terms of the size of the halo. And this scales weakly with halo mass to -0.1. So this is something I did with Andrea Macchio and Frank when I was in Zurich. And so this is the concentration mass relation as a function of different cosmologies, W map 1, 3, and 5. And so just the variation, these are all sort of standard LCDM, but even varying cosmological parameters by 5–10% makes a 10–20% difference on the structure of the halos. Okay, so this is all great, but there's a problem with all this work, and it's that they don't include baryons. Okay, so the question may ask, well then, so how do the baryons modify LCDM halos? Is this something you really need to worry about? The background is just some pictures of M82, which is blasting out an outflow. So many years ago, people realized that if galaxies just formed slowly and smoothly, basically adiabatically, then this parameter here, which is basically the specific angular momentum of dark matter particles, so r times v circuit, that radius, will be conserved. And then this leads to this so-called adiabatic contraction. And basically, you increase the dark matter density near the center of the galaxy where the baryons are condensing. And in some cases, you can get up to a factor of 10 increase in density. So this is quite a big effect. But then there's also, galaxy formation is probably not a smooth, slow accretion process. And so, for example, if the accretion of baryons is clumpy, then you can get the halo to expand. And so this is basically the baryons giving the orbital energy and angular momentum to the halo by dynamic friction. This is something that Emilio Zant showed, I think, when he was a CITA fellow here or around the time. So people have shown this in control simulations where they just throw in some test particles into a halo and watch it evolve. And also it's been seen in cosmological simulations. Although I note that both of these simulations, the net effect we find is the contraction. Because initially, at very early times, you have a dissipational process and the halo is contracting, and then at later times, you have bombardment with these minor mergers which start to pump the halo a little bit. So the other effect is feedback. So basically, at the same time that Julio wrote these papers on the universal halo profile, they wrote a paper about how this might not be universal. So basically, the idea is that if you remove a large fraction of the baryons from the center of a galaxy, and the baryons make up a significant amount of the mass, then you unbind the system and the halo will expand. More recently, people have shown that you actually don't have to have a very violent process. You can just perturb the potential in a time-varying way, and you can end up causing the halo to expand by similar amounts. So basically, the answer is theorists don't have a unique prediction for how halo respond to galaxy formation. And
to unbind it, you require mass output.
Yes.
It happens in an order that now becomes shorter, right?
Yeah. So the idea with the outflow is that you bring in the mass slowly, and you remove it really quickly.
Right. Is that realistic to move that much mass that quickly instead of dark matter?
Maybe not. I mean, so this was a toy model. This was a sort of a semi-toy model. And so in the simulations, when people do put in the feedback and try and get, they get mass outflows. The mass outflows, they explain why the galaxy formation is very inefficient. But the process which is making the halo expand is not the fact you've got a massive fast outflow. It's just that the perturbations are faster than the random time. And so the halo just doesn't really know always something. And so I just like to point out that all scales are affected, and especially dwarf galaxies. So often people like to study dwarf galaxies for studying dark matter because the baryons don't contribute so much to the potential. But these are ones where you really have to worry about things like feedback affecting the structure. Okay, so and then in terms of if you look at modified gravity, so if you just take the Mond paradigm, but the others are basically similar. So in Mond there's no dark matter. What is called the mass discrepancy, so this is the difference between the observed amount of mass and the mass you think in baryons. This is just used for local acceleration. So suppose you observe a rotation curve, then you have some interpolation function which tells you how to change gravity from turning into some Mondian or modified gravity regime, and then this will give you the circular velocity just through the baryons. So, for example, Mond would make a prediction for not just the baryonic mass in galaxy, but the distribution of that mass. So if you can measure the mass due to the baryons, then you can constrain this theory or constrain any other variance of this theory. And the reason why this is unknown is, well, you can observe the gas in galaxies, you can observe atomic gas. That's quite simple. You can observe CO, and you can infer molecular gas for some uncertainties. And you can observe luminosity, but to get the stellar mass, you need to know the stellar mass to ratio, which depends upon IMF. So that's basically what I was saying here. So we can observe a rotation curve. So this basically is mass as function of radius. And to measure the baryons, we can observe the gas, but the luminous component is just this big uncertainty that maybe is a factor of 3 or 4. So you can get around this IMF uncertainty just by looking at galaxies that the luminous component is subdominant to the gas, subdominant to the dark matter. Okay, so what do we know about the IMF? In the solar neighborhood, this has been measured, going back to Salpeter, and it's where the Salpeter slope comes from, the power law, the number of stars is a function of the mass. So the Milky Way just turns over below about the solar mass. And then using dynamics, you can get upper limits to stellar mass ratios. And so these disfavor in spiral galaxies and in fast rotating ellipticals, this disfavors the Salpeter IMF. The upper limit is somewhere between the Milky Way and Salpeter. More recently, there's been some constraints using stellar absorption lines that you only find in dwarf stars. And they found evidence in fairly central parts of massive ellipticals, that the IMF was even steeper than a torpedo. And this results in much higher stellar mass ratios, so more mass for a given magic velocity. And then in terms of evolution, a few years ago, people were pointing out that if you have a bottom-like IMF, so this turnover mass goes to a high redshift, moves to a higher mass, then you actually could help explain some discrepancies in the evolution of star formation rates and stellar masses. But these two, it's interesting that these two IMFs are completely inconsistent. So we don't really know how the IMF varies, but we know pretty much that it isn't universal. So just a summary of the key unknowns for testing dark matter using a galaxy structure. So we observe, or from theory, we know what the LCDM dark matter halo should be like, but we don't know how galaxy formation modifies dark matter halos. And we can observe total mass, but to get the dark matter content, we need to subtract the baryons, which in most galaxies depends on the IMF. And so the goal, and we'll only get partway through that in this talk, but is to understand, we'll hopefully understand simple recipes, simple physical processes that we can to understand how the halos respond and how the IMF varies. So if you pick a galaxy or a sample of galaxies of a given type, given mass, a given structure, you can predict how you can predict the IMF and the stellar masses, and you can predict how halo responds. Okay, so there'll be two parts. One is constraints and scaling relations, the other part strong lens. So scaling relations, so the two most famous ones are the Faber-Jackson and Tyler-Fisher relation, and these, since a few days ago, they have over 1,000 citations each. So they're important basically because they're linking something which is just due to the baryons, in this case the V-band magnitude, with something which is telling about potential, the baryons at dark matter. So for early types, you measure velocity dispersion, and for late types, you measure a line width or rotation curves from, in this case, these are from H1 spectra. So in the 70s, they had 20 so galaxies, and they got out these scaling relations. So now we can do this with Sloan. We have 100,000 galaxies. We can measure this relation. So now instead of luminosity using stellar mass, which has been derived from the photometry in Sloan, plus assuming an IMF, which in this case is Chabrier. And so we can observe curvature in relation. We can observe the scatter in this relation. And we're trying to actually put a model that can sort of reproduce this curvature. For late types, we have rotation velocity measured from the resolved rotation curve. And we don't have as many galaxies because it's much harder to measure rotation curves rather than these. For early types, you just get data from the fiber from Sloan. So you just have an aperture, whereas the rotation curve means you're going to split across the galaxy. Okay, so these are the fundamental scaling relations, and so at a given stellar mass, so we take a stellar mass 5 times 10 to the 10, which is basically the mass of the Milky Way in stars. Then for a late type, the average velocity is 190 kilometers a second. So you might already realize the Milky Way is supposed to be about 220, so it's already not typical in terms of spirals. And for an early type, we have a velocity dispersion of about 145 kilometers a second. And so the first thing is how do we convert this dispersion into a circuit velocity, or something that is related to mass? So I won't go into too many details, but basically, this is the relation we use. So if you measure a velocity dispersion within the effective radius, half-life radius of a galaxy, you multiply by 1.54 and you get the circuit velocity. So it's square root g over r, that radius. And this 1.54 is based upon strong lensing, because strong lensing gives you mass that's independent of dynamical state. And then there's some dynamical measurements which basically straddle this. So this uncertainty comes from various other measurements. Okay, so for a given stellar mass, we know the total mass within some aperture. And then, so we build these mass models. So the gas, so basically what we do is we have, for a given stellar mass from stellar models, we get an average rotation velocity or circuit velocity from these Tyler-Fisher Faber-Jackson relations. And then we're constructing average models. And So for a given stellar mass, we know the average gas mass is a function. There's a scaling relation there. We know the sizes of the stars, the distribution up to some normalization, which will depend on the IMF. And we know how to relate the distribution of the gas with the distribution of stars. There's another correlation there. For a given stellar mass, we know using weak lensing and static kinematics the mass of the halo. And from LCDM and cosmological simulations, we know how to do the structure of the halo to the halo mass. So we can compute these average models given the IMF and the halo response. And so putting these things on the, so we do this for early types and late types because we can measure these separately. So the shaded region is showing the data with the uncertainty due to the sigma. And so this is a model with uncertainty and halo mass, so it does a pretty good job. For the late types, and this was also using some similar work by Schultz et al. But for the late types, this is offset. So for a fixed stellar mass, the galaxies will decay too fast. This is something that I pointed out in 2007, and now we're sort of confirming this using bigger samples, better data. So the solution here is you either reduce the velocity, so you modify the halo response, or you reduce the stellar mass, which also changes the velocities, so it's not simply effectively shifting one without the other.
Yeah, I'm trying to understand. So you can measure the mass from length or large number of galaxies.
Yeah.
And you get a V total from that.
No, that just gives you, that maybe goes to maybe 50 kiloparsecs.
Okay.
It gives you the mass of large radii,
Right.
which you can fit a total halo mass,
Yeah.
and you might be able to get some constraint on the density profile,
Right.
or the structure of large radii. But in the center, you have the baryons.
I guess my confusion is that I'm not sure what part of it is actually the model. Like you have a bunch of observations. Right? Where is the model coming from? You say you're using the night and the albedo model.
Yeah. So if we give a stellar mass, we know the distribution of the baryons up to IMF. So we'll pick an IMF, and that will give us the circular velocity history of the stars and gas. And that'll look something in the curve, something like this. Then for a given stellar mass, we know the average star and halo mass.
I see.
And from the simulations, we know how to link the average mass with the average concentration.
Right.
So we know the structure of the halo prior to any baryons.
I see.
And then we can apply this model, which, so you need to know the initial distribution and final distribution of the baryons.
Right.
So we know the final distribution, we assume the initial baryon will mix with the halo,
Right.
and then you can calculate how the halo will respond.
Okay.
Yeah, so it's just two unknowns, and you have this extra constraint. So you still have a degeneracy because one constraint. And so, I mean, the reason why doing this average is an advantage is because for individual galaxies, you don't know, well, one, we can't measure individual halo masses. But even if we could, we still don't know the concentration of that individual halo. And also, the stellar masses, there's statistical uncertainties. So if you take a lot of measurements, then you end up, you get rid of the statistical uncertainty and satisfaction, which is basically that. Okay, so there's a degeneracy in the solutions here. And there's also, even for the early types, there's a degeneracy here, because you change the IMF, and then you have to change that halo response. So what we do is here, this is just the constraints we get from 0 points of these relations. So if we just take a Chabrier IMF, that's here, then these are modeled with different halo responses. So this is just a standard NFW halo that hasn't been modified by anything. And these are models which the halo retracts. So this is very weak contraction, and these are stronger contraction. This is an expanding halo. So if you have a Chabrier IMF, then you want something like this Gnedin 2004 halo retraction, which is slightly weaker than the standard model. Although within these error bars, which are dominated by the halo masses and the V of sigma, then it's still consistent. And then for a given halo contraction model, we'll just suppose that we assume that the cosmological simulation is completely correct, and that there's no halo response. And so for the early types, we need to have heavier masses by roughly a factor of 2 for the same IMF. Okay, so that's basically just summarized here. So we have the degeneracy between the IMF and halo response. So we know, at least we can say that the IMF and the halo response has to be different between early and late types. And for a given IMF, we need strong contraction in early types for late types. And if we have a given halo response, early types require heavier IMFs. And this at least seems consistent with if the IMF that was observed by Van Dutton and Conroy, which actually corresponds to something that's even heavier than torpedo. If this turns out to be the case, then it would imply that the halo response, both early types and late types, would have to expand. But it's possible that that could be a universal process, and just the IMF in spirals like the way Chabrier which we galaxies for some decent degree. Okay, so that's the first part of the talk. The second part is related to strong lensing. So this is a near-infrared image using adaptive optics of a spiral galaxy with the star forming green. And you may not be able to see the lens dark, so I've given it a highlight. You can see that it's. So initially this, well, I'll get to it. Initially this was discovered with an optical HST image, and so there were actually 3. It looked like a cusp configuration, but we think this is just because there's dust in the star forming ring, which causes you to change the apparent topology. Okay, so how can strong lensing help here? So there's 2 ways basically that strong lensing can help you measure stellar masses. So one of them, which has been applied fairly recently, is that microlensing of background quasars are sensitive to the amount of mass that's in very compact objects, such as stars, and more extended things such as dark matter. So although we think of dark matter in CDM as being hierarchical and very funky, on the scales of, so it's supposed to go down to, say, Earth masses. But these structures are so diffuse that they basically put them into a smooth distribution in terms of strong lensing. And so by looking at the microlensing, you can find the variability of the light curves, you can get some constraint on the amount of stellar mass in the line of sight of the observer. So this has been done on 10 galaxies, and there's some results I haven't quite digested yet. So what I'm going to talk about in this talk is basically it's using the geometry you get with strong lensing. And so in kinematics, you basically just get mass in spheres, or more correctly, you get mass in ellipsoids. But with strong lensing, you get mass in a cylinder in projection. And you also get, which is quite useful, you get the ellipticity of that mass. And so you get the ellipticity basically from the configuration of your lens. So if you have a quad and you have, well, I won't give details, but you get some constraint on the ellipticity that way. And the mass basically comes from the area inside the critical curve. So how does the ellipticity help? So if you imagine, and these are 2 cases, you imagine you have a galaxy disk that's face on, so it's circular on the sky. You have a spherical halo. Then if you, from the lensing, if you observe a lens that has a Q of 1, so Q is the axis ratio, A over B, then this means the halo has to be spherical. But if you observe a lens with a flattening, say, 0.6, then it means that you know your disk is round, you see it, so it means your halo actually has to be flat. And then if you take an edge on this, then if you observe a Q of 1, that means you know that this disk doesn't contribute any of the mass to the potential, so you have a darkening oriented system. And if you observe a Q lens which is basically equal to that of light, then it means that it will dominate by the disk. So that's just a picture of how having the ellipticity information can help you. In terms of, so how does the mass help you? Well, so there are these well-known degeneracies between bulge halo and distant halo, so these are described here. So this is circular velocity, the function of radius. So there's a few lines here. There's a red model and there's a black model. And so this line is the contribution to the circular velocity in the stars, so this is your focus profile. And the other dashed line is the contribution from the dark matter. And they add up to the solid red line. And then if you just lower the mass from the stars by a factor of 2, you get this line, and you can scale the parameters of halo to make it so this almost matches again. And then you can do the same thing for a disk. So you have a disk of stars and you have a Dutton halo, and you can scale the stellar mass by a factor of 2, and you can tune the halo, and you get pretty decent amount. So you can observe, if you observed this profile to arbitrary precision, it wouldn't give you any information to determine which of these two solutions was correct. Right. But, so this is the ratio between projected mass and the mass present in the sphere. So for the Bulge halo system, these should formally be identical, and it's easy to imagine why. So if you just take a field of ping pong, a sphere of ping pong balls, with some density distribution, and then you imagine having a cylinder and a sphere, and you measure the mass and the amount of ping pong balls in the cylinder versus the sphere, you get some number. And then you just paint some of the ping pong balls a different color, and let those be used the baryons and the dark matter. And then obviously you haven't moved any ping pong in and around, but so the ratio is going to be dependent on how you use the mass. But if you have a disk and a halo, there is a significant difference, about 20 or more percent in the ratio between projecting mass and spherical mass. So the projecting mass you can get from Sloan lensing, and the spherical mass you get from kinematics. So in principle, you have this, both the ellipticity and the mass gives you new information. So just a summary of how Sloan lensing help. Now we can turn the lights a little. Show some more pictures.
It's that one.
Okay. Okay, so if we have a, can we go back to what we had before? This is too dark. Okay, so if we have a distal-enabled lens, so here we have a spiral galaxy with a sort of disc-shaped bulge, and it's rusty here, and this is the multiple images. We get new information from the ellipticity and from the projected mass that helps us break the disk halo degeneracy. Whereas if we have a bulge-enabled lens like this one, and this is part of the R, even though it's in a spiral galaxy, there's a dust lane, there's actually two dust lanes, it's to it. There's an edge on this and there's sort of another one. This won't actually help us break the bulge halo degeneracy, because the lensing just tells us about the bulge mass. But what it does give us is an upper limit on the mass within this radius, and it gives us an independent dynamic state, which is important for galaxies like this, because there's going to be rotation and dispersion, and it's quite hard to disentangle to get a masses when you've got such complicated dynamics. Now, the problem of using this approach is that, say, 5 years ago, you could count the number of spiral galaxies on the fingers of one hand, and these ones, the ones that we know, that we're well studied, these are more like this object and this object. They're basically bulge dominated. So you kind of get some constraint. This is an edge-on galaxy, so you could show that the disk is submaximal and that it doesn't. The contribution of the disk to the dynamics is less than it could be, but you don't get really strong constraints on the mass of the disk. And so something that changed things recently, and also for elliptical galaxies, with the SLACS, the Sloan Lens ACS survey. And so this is just some images of all the strong lenses that they found. It's about 80 something. These are redshifts between 0.1 and 0.4 or so. And so you notice that some of these are actually quite distant. So there's a number of them that actually, and this is actually one we're going to study, a number of these are disks and actually fairly high information. And so we started this survey. Called Sloan Swells, this is a big swell wave. Sloan wide field camera 2, big 2. Edge on, so we want to find edge on disks, edge on lake type galaxies. So we use a similar method as the SLACS survey. We get, and most of the people are the same. We get redshifts. So we go to Sloan and you look at all the galaxies that have 2 redshifts. So you have a foreground, a low redshift, usually due to the stellar absorption lines, and you get a high redshift from emission lines. And then you follow up the promising candidates with HSPs, because Sloan has very bad resolution on these scales. You know, it's one arc second, and you really want 10 times better than that. And also we followed up with near-infrared imaging when we can with laser-based starlight optics. So that gives you 0.1 arc second resolution. And also we get some kinematics from CAD. So currently the data we're using, our sample, we have 8 A-grade lenses from SLACS. Let's see, there's this one. We've got 6 new ones from the Cycle 16 proposal, and we actually got 2 that we just got from the K-band only. So these 3 objects were observed only from the ground with adaptive optics, and we were able to confirm that these are strong lenses. So it's much better if you have HST, but if you can do this from the ground, there's no space option. So this was up to cycle 18, cycle 16. We observed 90 galaxies and we got 8 strong lenses, so 42% success rate, which is quite happy with that. And then these are just some pictures of some lenses or lens candidates from the cycle 18 program. So this is an edge on disk. Again, there's sort of 2 dust lanes, and we're not really sure what's going on there. Maybe there are 2 doubles here. This one we've saw before. There's an arc, and this is another edge on galaxy with an arc. And we've got another bulge lens. Like that one. This one, well, there's a point source here, and we know it's Richard 3, and there's a point source here which we don't know where it is exactly, but this may be a double, maybe it's a solution. But it's consistently, the color here is red compared to that, so consistent with being red through the dust mite. So this is sort of the sample we have, and the remainder of the talk I'm going to describe the analysis we have of the first galaxy we've finished. Okay, so this is 2141 0001. Okay, so if you go to Sloan, this is what you'll see. It's 5 arc seconds across, so you just get some quasi-elongated blob that's still red, and this is the spectrum. Most of these bumps and wriggles are actually real. This isn't noise. These are real features. These are absorption lines. And we get a redshift of 0.14 of the lens and the source. And actually the source is this little part here. So it's red, it looks disky, but we don't really know if it's going to go to HST, and so this is a snapshot image, so it's just one frame, and so these blobs here are called rays, but we can remove them cosmetic pieces, but we just here things they have. So you have the three images in their custom configuration, and if there's a counter image, it will probably be somewhere buried under the light of the bulge. The galaxy is disdominated, the fraction of light in the disk is involved is about 80%. It's high inclination and it's also distorted. So then we folded this up with PET. We've got a rotation curve, so this is H alpha, and this shows that we're starting in green, and the dust is, and we get quite a big line width. So the rotation velocity is at least 260 kilometers per second, and so the Milky Way is about 220. And this is similar to the M31. So this is sort of an M31 analog at redshift 0.14 instead of negative redshift. And then we've also kept, we've got this K-band image. And so now we have a much, the image is very, very smooth. So the advantage of K-band you see through the dust. And the arc, instead of being 3 pieces, is actually something that's quite continuous and smooth, which is telling us that this actually is. And we get a scale length and we get more information on what it is. So just using the K-band image and just using a simple lens model, so single isothermal ellipsoid, which is commonly used to model elliptical galaxies. You get a correlation here between circuit velocity and axis ratio. So this is the PDF of the model. So the axis ratio, the domestic axis ratio is about 0.42, and there's some degeneracy obviously with the circuit velocity. And if we compare this to the axis ratio of the stars, so the disk component is about 0.3 and the Bulge is about 0.5. And there's roughly equal contributions to the position of Bulge within the critical radius. So roughly speaking, the lens is being done by the stars. We'll go into more detail and actually do a model with 3 components of Bulge, disk, and a Dutton halo. And this is just an example image. This is a lens image show us. This is the rotation curve. So the points are data that we observe. We only use these points in the fit because what's happening here we're not entirely confident. We're modeling well, but in hindsight we model this quite well. But the reason is this is the intrinsic rotation curve, and then when you fold in the beam smearing and a little bit of inclination effects, then these velocities go from 300 down to 220. And the gaps are fairly enormous in the center. So these two models are just examples that are unconstrained in the center, and they give you the same thing. So it's basically 4 parameters and 8 parameters we're interested in. These are the distributions of these parameters with the histograms of the PDF. So the red curve is the prior here, and then the solid is the marginalized posterior. So I'll go through these things one by one, but basically the good thing is that all of these parameters are more tightly constrained by priors. So the first thing I'll mention about is the stellar mass. Okay, so using stellar population models, we get a stellar mass of 10 to 11. For the Chabrier IMF, we get slightly higher for 0.22x higher for the Stellar IMF. And these are shown by these histograms. But from the lensing kinematics, we get this distribution which has a median of 10 to 11 with these uncertainties, so that there's a marginal favor of Chabrier IMF. But the thing is here, this mass we get from lensing kinematics is really a baryonic mass in some sense, because we're assuming there's no cold gas in this case. But when we put in the cold gas, this will say. So from the scaling relations I showed earlier, we know that for a stellar mass of about 10 to the 11, using Chabrier IMF, then there's about 2 times 10 to the 10 solar masses of gas in the galaxy. So some of that gas will be distributed like the star, some of it may be more extended, and so we get some uncertainty here. But this will shift down all of these masses by at least 0.1x. And then instead of a marginal favor in this IMF, you really strongly favor a Chabrier IMF or a salpedo. And if you want us to say what's an IMF in between these two, then the salpedo IMF that Eric Bell and Dutton came up is also much strongly favored over Chabrier, but distinguishing between Chabrier and salpedo is quite different. Okay, so according then, if this galaxy was a typical spiral, then according to the stuff I presented earlier, then we should find that the halo is expanded, because that was the conclusion we had earlier. But it turns out actually that this halo is actually much denser than we expect. And so, so one way of characterizing the structure of the halo is just using this delta V2 parameter. So it's defined as the mean density inside with respect to the critical density of the universe of the dark matter halo. So within a radius where the circular velocity is half the maximum. So you take some rotation curve profile, you find the maximum, and you go to Vmax over 2, and you find that radius, and then you set Vmax squared over R squared. And so if we look at from cross-model simulations, we get this black line in the shaded region shows the 1 and 2 sigma scatter intrinsic, and these points are just from dwarf galaxies, which had the baryons subtracted off. It's not a huge effect, but it does slightly affect the results. And then this is the distribution from the posterior we have from our Sloan Lens. And so the median value is quite a bit higher than you would expect, although there's a tail down 1 sigma, it's not too far away. But just taking this, naively, this is the density of this halo is much higher than we would expect. So this means that either this is evidence that this halo is contracted, or there's a early formation bias, and this early formation bias comes out because in LCDM, the halos that are up here form earlier than the halos that are down here. And so the explanation for why this is inconsistent with the results I showed earlier is that this galaxy is offset from the entirely Fisher direction. So like the Milky Way, it rotates faster for its mass than a typical galaxy. It's slightly denser in terms of the stars than typical galaxies, but so it makes sense that we'd expect to have a dense halo. Okay, so finally I will just say something about the shapes. So in LCDM, the Dutton halos are triaxial. And this is just a picture of a cluster from the lens simulation, so you see it's quite almost 2 to 1 axis ratio. So axis ratio is about 0.6 to 0.8. And again, the problem is galaxy formation changes all of this. So the halo gets sphericalized, and instead of being sort of more prolate, these lancine halos are roughly prolate, they become more oblate. And again, this is sort of sensitive to the amount of baryons you put into a galaxy. If you put in a lot of baryons, then if the baryons turn into a sphere, then the halo will look more spherical. If you put in very few baryons and then in a disk, then the effect of the halo is much weaker.
So the boundary defining CO gray? Sorry? What is the boundary you're using to define CO gray?
Okay, so in simulations, well, that's a good point actually. So in the simulations, you can measure this within the virial radius.
What's your definition of the virial radius?
Well, this would have been 200 times the virial density, 100 times. So if you measure this, the point is, the halos are actually more prolate towards the centers. So if you observe this within 0.3 of the virial radius, then this number will go down to 0.55. So okay, slightly more.
But is this now?
This is which is 0, yes.
So it's 200 now? Okay.
What do you mean, 200?
Well, it's just that we've got a lot of repensation occurred in galaxies now. Oh, really? And the halos.
Yeah, the halos are more contraxial in the inner regions than the outer regions. But the point is that the galaxy formation is going to change with this, and especially towards the centers. But actually, I think in these simulations they found that even out to a significant fraction of the radius, the shape has changed by having baryons and density. And so in our galaxy, we have some kind of law we're talking about prior, so we can't say for sure that these objects are very, very. What we can say is that halos are very prolate. So it's prolate. So it's sort of a definition here. So if we were to turn this prolate, if we assume this halo is prolate, then this Sierra A turns into 1 over that, so it turns into 1.7. So halos like that are very strongly ruled out. And we get a preference for something that's roughly spherical. Okay, so in summary, so if you want to understand the structure of the nature of dark matter from the structure of dark matter halos, you need to understand these two issues. So from the scaling relations, we find that the halo contraction and the IMF both cannot be universal. So there'll be something interesting has to be understood. And then depending if you think the IMF is universal or halo is constantly universal, then these are some constraints. So strong lensing provides some unique information that you don't get from any other method. You get projected mass and ellipticity. And then analyzing this spiral galaxy lens, we strongly favor Chabrier IMF over CITA IMF. So this is basically consistent with the Milky Way. And stay tuned, we're analyzing more spiral galaxies. So just a few words about the future. So far, I was just talking about the mean relations, but the scale relation has scatter, and the scatter in one relation can be correlated with that of another. And so for elliptical galaxies, this is the fundamental plane. You take the size mass and velocity dispersion mass relations, these are coupled. And understanding the coupling can tell you about the distribution of mass in stars and dark matter. Strong lensing, there's a lot of potential here because our study, well, we've done 1 galaxy, we might be able to do 3 or 4 more. And the micro lensing, they've done 10 galaxies, 10 lenses. And so we want to find more lenses, and LCDM is going to do a great job of finding hundreds of lenses. And if we had spiral lenses that were quad QSOs, then you could use the microlensing and use the geometry with kinematics. And because, so one of the problems we have is dealing with the dust, and Alma is going to be really, really great for this because you get high spatial resolution imaging, so you can get an image of the background objects without worrying about dust or star formation in the lens galaxy. You get kinematics that is quite high resolution, and you also get molecular gas mass of the lens, which is important if you want to get a detailed constraint on the mass in the stars rather than just mass variation of the gas. Okay, so I'll stop there.
Time for a few questions.
So in the first part of the talk, we talked about this degeneracy between the halo contraction and the IMF.
Yeah.
So I was wondering, observations of dwarf galaxies and LCDM galaxies show that it is a coarse profile. So there must be some way to get benefits of the cost.
Yes.
So is that consistent, or is that an extra constraint in this halo contraction?
Yes, so that will be consistent with the idea that that spiral galaxies, the halos have to expand, even if it's the Milky Way or if it's a dwarf galaxy. So there was this, you can understand, so these feedback models that I mentioned. These simulations by Chabrier Dutton, they create cores in the dwarf galaxies, and they compare those to observed galaxies, and they're quite consistent. So at least this process can turn possibly dark matter halos, as predicted by LCDM, into halos that are consistent with observations. But right now they haven't, just due to computational time, haven't been able to run the simulations with the same resolution for more massive galaxies like Milky Way. But then, I mean, people do simulate the Milky Way, but it's still hard to get exactly the right answer.
Are there more questions? No. Let's thank